This is a production of Cornell University.
All right, so we've got these polypedons, soil individuals, the map unit themselves. Okay, we have a whole set of map units, or the mapping units. Put them in context, okay? Now, what does the soil survey provide information-wise for these individual polypedons, or the soil individuals? The map units, okay? Well, all the things that you potentially can do in the field, and some of these you have done already. You've already done color, you've done pH. But we talk about soil thickness, we talk about salinity, structure, water availability, engineering properties, textures. These are observable physical and chemical characteristics. These are not interpretations. These are measured characteristics. It is from these measured characteristics that we then basically start predicting capacities. Okay, so we've got these the properties of the soil map units. We have their position in the landscape. Okay, we also can tell you what percentage of the landscape that individual occupies. And then, because we have these measured characteristics, we can make interpretations. We can give you capacities, how much yield you're going to get, how much water infiltration you're going to get, how much gravel you're going to get if you're going to build a gravel mine. Does that make sense? Yeah? Okay, infiltration for septic. All of these things that you might want to use on these soils. Okay? You now know where they are, and you know how much of the landscape you have of it. Which then gives us to how we can in fact use this. Yes, we make lots of great interpretations. But it's dependent upon how refined the map actually is. Okay? And that brings us to scales. Okay? The scale of the map is basically the ratio of the length on the map to the length of distance on the ground. Okay? So if I have a scale that means 101 to 20,000, that means 1 centimeter on my map equals 20,000 centimeters in the real world. That's my scale, 1 to 20,000. Okay? Now, a small scale map is actually a really large number, 1 to 1 million. Which is the smaller fraction, this versus this? A small fraction is 1 to 1 million versus 1 to 10,000. This is a small scale map. This is a large scale map. The easy way to remember this is a small scale map, objects look smaller. A large scale map, objects look larger. This is always counterintuitive because people think, oh, a small scale map, that means I can see sort of like the entire United States. Okay? Small scale maps, you see things very small. Large scale means large. Okay? So in this case, I could see a map of the entire United States. Now, if I have a soil map of the entire United States, and think about the scale of that, okay, it's right here. This is the map of the United States. What types of interpretations do you think I can make about my backyard? Nothing. On the other hand, this is my map, and it's an extremely large-scale map. Okay, let's make it 1 to 10. What kind of interpretations can I make about my backyard? A lot. But what kind of interpretations can I make about the United States? Okay, so the scale of the map determines what type of interpretations you can make. Okay, we call this actually soil order. Okay, soil surveys can be conducted at a lot of different scales. We call this orders. Okay, and these range basically from first to fifth order, with fifth order being the smallest scaled, i.e. the least detailed. Okay, the order scale of the soil survey basically influences the map unit. Okay, if I was trying to map the entire United States, I would not be able to map that unit of arcport, that deltaic sand, for example. Does that make sense? All right. So give you some idea about what these scales mean and the size of the map units and basically its use. Okay, orders across the top, fifth through 1, first. Scale, we're looking at 100 to 250,000 or 1 to 1,000. Okay, interpretation-wise, if I'm looking at the entire country or a county or a state, I can use it as a resource inventory. At this end, I can basically use it for management of that site. Does that make sense? Pretty straightforward? Okay. All right, so let's get back to these map units. So here's that cartoon again. All map units are not necessarily the same. Okay, and it has a lot to do with it has a lot to do with the scale, but it also has to do with the nature of the material or the soils or the properties that you're looking at within the scale. Okay, a soil phase, these could in fact be soil phases. Okay, a soil phase is used to characterize some sort of special feature of that particular map unit. Okay, I could have 4 or 5 arc ports across the landscape, and they are all arc ports. But for one reason or another, one of those arc ports is different. Imagine the top of the soil got scalped. Somebody came in for whatever reason and mined all the silt off the top. Okay, that arc port is still an arc port, but there's something special about that arc port. We would call that a phase. You guys will be meeting a phase next week, because you're going to meet one of the Martin phases. And then in 2 weeks or 3 weeks after that, you're going to meet a Hudson. That's a special phase. Okay? The Martin version, Martin is typically an agricultural soil, but we have a Martin that's basically under forest. Okay? The timber was cut, but it was never plowed. It does not have an AP. But when you look at the description for Martin soils, it's always an AP. Well, I have a soil that doesn't have an AP, yet it is still a Martin soil. That would be a phase of Martin. Does that make sense? Okay. We also have what we call consociations, where at least 50% of that map unit represents that soil series, with less than 15% representing a contrasting soil. You can certainly imagine scenarios where the soils are the scale that we're looking at is so fine, and the variation between soil types is so tight that we theoretically cannot, well, we could, but from a mapping sense, it's not logistically possible to map every individual contrasting soil within that area. Does that make sense? Okay. Yet, we still want to have some understanding of what's going on in that area. That's what we would call a consociation. Okay. I have 50% of this map unit is exactly what I say it is. But I know that there is something wrong. There's at least 15% or less than 15% of some sort of contrasting soil that is not going to interpret the same way. Does that make sense? Okay. We also have complexes where we have contrasting soils that consistently occur in a very intricate pattern, a pattern so intricate that we can't map it. And then we also have associations where we have general groupings of soils that are typically occur together in that landscape. Okay? This is an association map for Tompkins County. Okay? All these different codes, these colors, are not an individual soil. They're a grouping of soils that typically are found together in this area of the landscape. Okay? As you go farther north in Tompkins County, we find sweeter soils or soils that have a higher pH. As you go south in the county and into the higher elevations, we tend to find more acidic soils. Okay? Not all of these soils, not all these acid soils are the same soil, but they are all acid soils. Not all of these soils up here are alkaline soils, are the same soil, but they all tend to be alkaline. Does that make sense? Okay. Another way of looking at this is this. This is a Chester-Glenelg association. This is from Maryland. But basically, you're looking at a landscape concept. This is where these soils are found in this landscape. Higher elevations, Chester, going down into Manors on the edges. Some Glenelgs at shallower slopes, going all the way down into these Bales and the Hatboroughs. And there's a couple more Glenelgs up on the sides. So there's side slopes, Glenelgs down steeper, and down at the bottoms, we're looking at Manors, and the Hatboroughs and Bales down at the very bottom. Okay? This is not a soil map. This is a concept of how these soils are arranged in space, though. This is the association. This is how they are associated. Does that make sense? Let's get another one. Okay, this is another Maryland one. This is sassafras. This is the sassafras Woodston association. Sassafras tends to be up in these upper elevations. Woodston basically sits in the first terrace down into Fallingstone, and then you basically get down into these tidal marshes. And sometimes you're going to find a matta peak on the side slopes. These are all alluvial lands and tidal marshes, basically overlying sandy soils. Go.
Do you get this in other landscapes? So can you make sassafras, Woodston, Fallingstone in like a montane landscape?
No, you won't. This is just in this type of landscape. Okay, so this is the coastal plain of basically the East Coast.
And it's only ever going to be that specific coastal plain?
It's only going to, you're going to find other soils in here, but these soils are only going to be found in that kind of coastal plain. Basically from Maryland all the way down to, I guess, potentially Florida.
So basically these three guys made their own series for the East Coast? Or something.
These three guys?
Sassafras, Woodston, and Fallingstone.
These three soils.
Soils, okay.
Yeah. These are individual soil series. These are individual map units. These map units tend to be found together in this association. So this is the association of the Sassafras, Woodston, and Fallingstone.
How do you standardize all these differently named associations?
Oh, where the name comes from?
Like, I mean, coupling this landscape with something on the West Coast.
Well, the West Coast would have these types of associations as well, but they would be different soils. And you got to imagine, let's go back to those 5 soil forming factors and the processes, and then the parent materials and the weathering. The parent materials that are here, these are sandy sediments, are going to be slightly different or dramatically different than what you see in the West Coast. Okay? And different parts of the West Coast, you start getting to the higher elevations versus the lower elevations, you get into the valley versus the mountain edges, you're going to have different types of combinations of the 5 soil forming factors and the 4 processes acting upon them. And you're going to produce, I mean, here, this is, I've showed you, these are both Marylands. Okay? Well, this is to the north of us. Different parent material, shale sandstone with glacial limestone, shale tills, honeoy, our state soil, lima on the edges, candea, palmyra and eel, palmyra and Phelps. This is that association. And you can see, if you look at the parent materials, here's a hollow with lions in it. Okay, here's the eels. They're basically sitting on recent alluvium. Those palmyras and Phelps on this side are basically sitting on gravel. Okay, the stuff that's up here, the candea, lima, honeoy, are basically looking at limestone and shale tills. Does that make sense? Okay, here's another sequence, and this is northern Tompkins County basically, and here's southern Tompkins County. Okay, we're out of those limestone tills. Remember this map. Remember this map. Okay, that's the sediment. Those are the parent materials that are forming that. This is the southern part of it. Okay, so northern part, limestone glacial tills. Southern part, sandstone, glacial till, no limestone anymore. Okay, Martin sitting up the ridges, moving down to Lordston, Erie, Langford, Bath, and Valois, Phelps and Howard down in the bottom with the gravels. Okay, sometimes we'll get some freedoms down here. Sometimes we'll actually get some eels as well. And then up in the hollows, up at the tops, we get Volusias and Tullers. This is not a map. This is a concept of where these soils will be found on that landscape. Those are the associations. This is a map. But this, all right, so let's do this one. This, the blue, is that. Does that make sense to everybody? Okay. This is where we're going to be going next week. See the ponds down here? High elevation right here. Ponds down here. High elevations up here. Martins, Volusias up in here. Langford, Bath, Erie's down into the sediments down the bottom. Does that make sense? Now you can transfer this directly to that and make a map. Okay? This happens to be the Martin series. These are basically the slope aspects of this association. Does that make sense to everybody? Do we feel fairly comfortable with this at this point? Go. Generally, it's topography. It's like a topo sequence. Off the top of my head, I can't really think of anything other than it. But it's not just the topography, it's how the drainage is working, and also huge what these parent materials are. I mean, and this is a good example. You know, it's shallow here is these Lordstown on the shoulders. But it starts getting deep at the top and the bottoms, and you start getting into these guys. But the minute you move that parent material, now this parent material is certainly being driven by the bedrock and the topography. I mean, it's not like water doesn't flow downhill. You know, you're going to get that type of material down there. And if you get that type of material down there, you tend to find these types of soils down there. Okay, other questions? I mean, this is, you know, this is kind of cool if you think about it. Because in essence, we are mapping a concept. In fact, that's what soil survey is, or that's what the technique is. We basically develop a concept of how these soils are arranged in space. Because the truth is, we cannot put a hole every place on the planet. We cannot physically map every spot. So what we do is we build up these concepts of how these soils are arranged, and then we test them. And we constantly test them. And then what we go out is we look at a real landscape and say, is this association working? Is this concept working? Not the association. Is the concept working? And then we figure out where those break lines, those break points are, and we draw the line. And then we test those lines, make sure the lines are in fact where we expect them to be, and the soils on each side of it are what we expect it to be. Fit within those range of characteristics that is characteristic of that pedon and that soil individual. And then we call it a map unit. Does that make sense?
This has been a production of Cornell University, on the web at cornell.edu.